Hello, good afternoon, everyone, and welcome to the first episode of France is AI Talks. I'm Julia Fennert, Head of European Affairs at France Digital and coordinator of our AI task force. Most of you already know France Digital is the largest startup association in Europe, and every year we organize France is AI conference in Paris. Last year, together with the Paris Artificial Intelligence Research Institute, PRAIRIE, we had more than 70 speakers, 4,000 participants, and 300 meetings between startups and investors or potential buyers. And today we're thrilled to continue this collaboration between France Digital and PRAIRIE by launching the France is AI Talks. So stay tuned. We will return every month for exclusive talks with renowned researchers and to gather together the whole French AI ecosystem, researchers, CTOs, startups, and large groups. If you want to tweet, please use the hashtag FranceIsAI. You can use the hashtag PRAIRIE. I'll put everything in the chat for you, and please use the chat and the question feature on Livestorm. Without further ado, I would like to give the floor to Isabelle Rille, Director of PRAIRIE, who will have the honor to interview our distinguished guest, Professor Martial Hebert.
Thank you, Julia. So, hello, everybody. We are very pleased to have you here today. We are very happy to launch this new webinar series with France Digital. And we will have talks from AI stars of the French diaspora everywhere in the world. And this is my great pleasure to introduce today our first speaker, Martial Hebert. Martial is a professor of robotics at Carnegie-Mellon University. He was the director of the Robotics Institute from 2014 to 2019, and he is currently the dean of the prestigious School of Computer Science at Carnegie-Mellon University. So first of all, Martial, what are your research interests?
Well, first of all, thank you, Isabel. Can you hear me okay?
Perfect.
All right. Good morning from Pittsburgh, from my office at Carnegie-Mellon University. My research interests are in computer vision. At the beginning of my career, specifically computer vision applied to autonomous systems, ground robots and autonomous robots. And more recently, I've been interested in reducing supervision in machine learning, in particular for computer vision tasks.
So thank you. And very briefly, where did you study? What is your career path? How did you arrive at this position?
I studied initially at ENS Cachan in mathematics, and then did a doctorate at what used to be University of Orsay. And I did research for my doctorate at INRIA in computer vision in specifically 3D object recognition. Then I arrived at CMU as a postdoc in 1984. I worked on, as part of a large team, in the first project on what is now known, the first federally funded project on what is now known self-driving. It was called the Autonomous Land Vehicle Project.
So thank you. And so last question, what is so unique about CMU?
Well, basically three things. And in fact, to show those three things, let me share my screen. So we all cross our fingers that technology is going to work. Okay, can you see it?
Perfect.
Okay, let me just magnify it like this. Good. Okay. So basically, three things are unique here, and in particular, unique in the School of Computer Science. The first one is illustrated on this slide here. What this shows is the set of 7 departments that compose the School of Computer Science. That includes basic fundamentals of computer science, machine learning, human interaction, language technology, robotics, software, and even computational biology. So just the titles of the department gives you an idea of my first point, which is that we take a very broad view of computer science and basically encompassing all of the components of computer science, reaching out very far. For example, we work with biologists in computer biology department to design the next generation of AI for genomics, for example. We worked with social scientists and psychologists in the human-computer interaction department. So there is this notion of taking a very broad intellectual view of the field. The second thing is the idea of leading the development of the field. Most of the names that you see here on this slide were the first. We are the first school of computer science, the first machine learning department, the first robotics institute in 1979. We have more recently the first program degree in computer vision, the first major in AI, in automated science, and so forth. So this is not to brag about a long list of first, but this is more to point out this notion of being able to create new things at CMU, that freedom to create new things. The next things that the next thing, and the third thing that I want to mention is this idea of being able to go from the most basic theory, right? Algorithmic theory, theory of machine learning systems, and so forth, all the way to integrated system. This is an example. This is a slightly older example here, but this is a fully autonomous system that has driven from tens of thousands of miles, and it actually has been deployed as a product. This was developed at a place called NREC, National Robotics Engineering Center, which is part of our school, where this is a large facility which basically enabled this integration of research. This is, by the way, another example of the kind of work that we do. This one is in the context of drones and high-speed drones. This is also part of one of our startups. Now, those examples that I show right here are in the context of robotics and autonomous systems. But of course, a lot of the work that we do also has to do with human interaction. This is an example here from Professor Heini Admoni, and showing some experiments in shared autonomy between a person and an AI system observing the person and trying to understand her intent and trying to use that information to help with the task. This is another example in the same vein for Professor Quistitani, which is to, again, being able to forecast intent of the person by, in this case, a pedestrian, in being able to predict in the future path of this person with all the applications that you can imagine for self-driving and so forth. So that gives you an idea of this breadth that we can have from the basic to the fully integrated system across many disciplines. And on the last point about this, what I just said about across many disciplines, just to show you how far this can go, let me just mention one last example, which is from Professor Ray Ghani and the School of Computer Science. And this has nothing to do with robotics. This has to do with AI for policy making. And the questions that you see here listed on the slide are all correspond to actual projects with local, state, or federal governments in basically trying to use AI to make better decisions for people. So again, this is just to illustrate the breadth of the research and the breadth of the level of research in terms of basic to integration. And I apologize, that was a very long-winded answer, but I am passionate about my school.
Oh, thank you. It was perfect. So just before starting your talk, I just would like to ask you, can you hide the button, the tools on the top of your PowerPoint to have a little bit larger screen?
Hide the bottom of the tools. Let's see.
There is a small arrow just at right and top.
At the right, okay. No, that doesn't do that. Okay. There are all kind of jokes about. No. Oh, you mean the one at the top? Yeah,
Yeah.
Sorry, I misunderstood.
Perfect, thank you.
Sorry, I'm slow.
Now we will just hear you, so I give you the floor.
Thank you. Well, again, thank you for the opportunity this morning or this afternoon for most people on the line, I assume. So actually staying on this slide for just 30 more seconds, the thing that is in common, the point that is in common across all of those systems on this slide is that any failure of those systems is catastrophic. This is obvious for the autonomous robot system. It's not so obvious for the AI for policy making system, but sometimes people forget the catastrophic impact that poor designs of those systems can have on people. In fact, you know, a misguided view sometimes is to say, well, I have data, I have, you know, pretty performant machine learning AI tools. Why don't I put those two together and use the output to make decisions? Just doing that is almost guaranteed to lead to catastrophic results. Okay, so the common theme across all of those, to be able to actually use them, is to be able to make them robust and trustable. So that's what I want to talk about today a little bit. And I'm not going to pretend that I'm going to present solutions to those problems, but at least give you a flavor of the kind of research and the kind of topics that we are looking into. So for that, let me just give you my absolutely the most simplistic view of what we do in a typical AI system. So we have basically a training phase or an offline phase where we have data, examples, rules, a description of the operating environment that we expect. Okay, in computer vision, that would be typically lots of images or videos from a particular task that we can train on. Okay, so we do some training and we get a model. Now, in this context, I should emphasize that when I say training, I don't necessarily mean learning a deep network. Training in this case may be designing the best planner for, or the best decision reasoning system for a particular application, okay, based on the data, the offline data. Now, once we have this model, we can use it at execution time. We have some input, in computer vision context, this would be an image, and we produce an output. Again, in computer vision, that would be maybe detecting the location of detected objects. For an autonomous system, this might be the path that the robot should follow at the next time instant, and so forth. Okay, so this is, again, extremely simplified on purpose view of what's going on. Now, when we do that, we make a number of implicit assumptions. All right. The first assumption that we make is that there is sufficient information in those training conditions that we had at training time. There is sufficient information to learn a model that is actually meaningful. The second assumption that we make is that the model that we get is actually somehow verifiable. We can somehow you know, evaluate the performance of that model and you know, feel good about it. And the corollary of this is that the model is robust to deviations from training conditions. So if now at execution time, my input is different from what I observed at training time, I have some confidence that the model is still going to operate in a reasonable way on that input. Now, in addition to that, another assumption that is implicit, maybe never really explicitly stated, is that if my input at execution time is sufficiently far, right, the model cannot operate properly. But I'm assuming that I can, you know, detect such a large deviation. In other words, the implicit assumption is like, well, if my input is too far from what I observed before, I have ways to detect that, and I have ways to not trust the model in that case. At least that's the implicit assumption. And of course, now this one is also obvious. Kind of by definition, we kind of assume that training procedure, whatever it is optimizing the right matrix, right, the right function for the task that we're actually trying to achieve. Now, that sounds like a completely obvious statement, right? If I train a system to do X, I'm assuming that, you know, whatever I'm optimizing is good for doing X, right? All right, and finally, again, kind of obvious, the model is able to capture, sorry for the typo, to capture all of the operating condition, and more precisely that we have a model that is powerful enough to deal with all of those operating conditions. So those are the implicit assumptions that we all use basically in building this system. The basic problem is that none of those assumptions are satisfied. In fact, most of them, not only they're not satisfied, we don't even know how to address them, okay? So why is that important? Well, it's important because in the systems that you saw earlier, that drone flying at high speed or that completely autonomous giant truck there, any failure in each of those 6 areas will lead to catastrophic result of catastrophic failure of the system. So what I want to talk about is some ideas on how to address those problems. And again, I'm not going to claim, magic solutions or anything like this. This is just a conversation to give you an idea of the kind of topics that we look at. Now, sometimes those topics are a little bit waved away under the heading of, capacity of the model or generalization, right? The idea being that if we have a model architecture that is rich enough, has enough capacity or whatever terminology you want to use, then it should be able to handle those things. In other words, it should be able to take care of input that deviates from the training data, should be able to be characterized or detect anomalies. The fact is that for the most part, those things have nothing to do with generalization or capacity, right? Those things require a completely new approaches. Those things require new tools, and that's what I'm going to try to talk about. Not about better deep learning architecture or more powerful learning method, but more how to address some of those problems. Okay, so let's look at one problem, which is the issue of having sufficient information in training conditions. Basically, what that is the issue that relying on very large scale curated, annotated data is not sustainable, right? Because in most applications, one needs to retrain the system with limited data. One doesn't have the luxury of generating all that labeled data. And in fact, even in one could, in many cases, most of the tasks that we're interested in will have naturally few examples. This is the classical view, in particular in computer vision, that most objects, for example, have very few occurrences and therefore very limited training data, and very few types of objects will have lots of training data. So we need to address that problem of limited training data. So let's go back to our the mother of all simple view of machine learning, where we have lots of input training data. What we would like to do is to be able to train with very limited data, perhaps only one example. Now, some information has to come from somewhere to do that, not just from that one example. The way we get additional information is the following. Instead of looking only as this process of going from the training data to the model, we want to also consider earlier tasks. So let's say that I've trained the system from many tasks, many examples of tasks, n example in this case, each with their own testing set and training set. by doing this, implicitly, I'm learning something from this prior experience. And basically, hopefully, learning something about how, for this particular task, the training works on many examples. And then I can transfer this experience to my new situation where I have limited data. Now, this is still very abstract, so let me give you two examples of work that we've done recently. This is work in my group with Yusheng Wang in particular. So I'll mention two ideas. One idea is to say, well, the model that we learn from limited data is not very good, right? Because we have limited data. So one idea is to say, well, why don't I take this model and somehow learn how to fix that model, right? How to tweak that model so that I get a better model that's closer to what I would have gotten from lots of data. So graphically, again, this is a very high-level view of this. Let's look at a simple scene classification problem. If we want to train a model from a single input, we're going to have a poor model. And a model in this context is basically a set of numbers. It's a set of weights, for example, for deep learning approach. So we can think of that model living in some high-dimensional space like this. Now, if we had trained the model on a lot of data, we would have gotten a different model at some different point in that space. So the idea here is to say, well, maybe if I have observed enough of those situations meaning low data on one hand and large data on the other hand, maybe I can say something about how I can transfer from one to the other. Okay, so that's the basic idea. Now, of course, that transformation itself needs to be learned on lots of tasks, but maybe it's possible to basically be able to fix that model to be closer to what we would have gotten from lots of examples. So this is how it looks like. At training time, we have a lot of pairs of tasks with few examples and the same task with a large training set. And we can, from that, try to figure out a strategy to adapt the weights from one to the other. Okay, and then at execution time, we simply train the system from few samples and try to adjust that model. This is example of of what happens on a classical object detection task in computer vision. The blue and green curve show the baseline approach, and the red one shows what we can do with this kind of approach. So, in particular, with the very small number of training examples, we see a very large improvement in performance. So that's one idea. One interesting thing about this kind of idea is that it opens the door to doing something that is very natural, which is to say, well, why don't I use the task for which I have a lot of training data to help me do better on the task for which I have very little training data, right? It's a very natural kind of approach to those kind of problems. So this is an example here on a very challenging data set with about 3,000, actually not about, with 3,000 classes. The classes are ordered from left to right from those classes with the largest number of training example. That's the blue curve. And going from about 3,500 examples for the largest classes to, at the bottom right, basically one example per class. The orange graph here shows the increase in performance by using the technique that I just showed, meaning using the task for those classes that have lots of training examples to figure out how to improve the performance on those classes that have few examples by learning that transformation. And you can see that it has the kind of behavior that you would hope and that you would expect, which is that you see basically no change, very little change on those easy classes, the one where you have lots of examples, and you see a large improvement on those classes where you have very few examples. So again, not a solution to everything, but simply to point out the kind of ideas that we can look at to address this kind of natural behavior of addressing this long tail of few example classes with those examples that have lots of examples. Okay, so that was one idea. The second idea, and again, it's just a class of ideas, not a single approach, is instead of fixing the model, let's fix the training sample, right? The problem is that I don't have enough training samples. So what I'm going to do is that I'm going to try to generate new training samples to fix that problem. So that's the idea here. Let's say we have 3 classes. We have few training samples. We get those separation boundary graphically, just to illustrate the idea. What we could do is to generate somehow new training samples, the one shown in the bright colors here, to add new training samples, and now we can adjust accordingly the decision boundaries to better reflect the actual classes. So this is one sketch of how we could do that. And again, there are many different ways of doing this. I don't claim that this is the best one, but this is again just to give you a flavor of the kind of things that we can look at. So in this approach, we start with a small number of training samples. That's our problem. But the difference with before is that we're going to try to generate through a generator new training samples. So that generator takes one training samples as input and a noise input to generate a completely new training sample that did not exist before. We can combine those 2 training sets, the real one and the new generated one, to then train a model for that task, which will output with some performance on some test set. The important point here is that we can then train this kind of system, by backpropagating all the way to the generator. In other words, the higher the bit of this diagram, of this approach, is simply to say that we can think of training the generator so that it is most helpful in generating new example that will help in the target task. Okay, so that's basically this idea, right? Learning how to generate those, hallucinate those new examples. And you can do all kind of quantitative evaluation that show that you see a large improvement in performance. This is an example here on a classical image classification task where you can see this improvement. This is one shot, meaning only one example on the left. All right, so those were just a couple of ideas. Of course, there's a lot of work in this area, but just a couple of ideas to emphasize what are the issues in this area of limited supervision. The second area that I mentioned is a little bit different. It's this idea that given that we've trained a model, we would like to be able to have some kind of predictable performance of the model, and perhaps more importantly, some way of verifying the performance of the model. Okay. Now, in classical engineering, that is not a particularly novel idea, right? In classical engineering, you would always do things like taking the model and certifying that within some operating condition, the output of the model is within some envelope, some operating envelope. So that's the most basic idea in engineering. The problem, of course, is that with the tools that we use in machine learning, in particular deep learning, it is very difficult to do, and still very much of an open problem. So let me show you a couple of ideas about that. This is the work of Professor Chen-Lu Yu in the School of Computer Science. And let me just set the stage again. Her work is in the context of robotics. So this example shows learning for precision insertion. So basically learning parameters for precision insertion. The middle one, I'll show you a better video later of the middle one, but is basically understanding human assembly. and in particular being able to do motion prediction and being able to predict assembly tasks from observation. And the third one is basically robot-human interaction. This is an example here. In this particular example, the robot system observes the person, reacts to their activities to be able to still achieve a task. The key point here, of course, is that this robot is, of course, like any robot, a dangerous machine, and the system that is used in there has to be verified, certified in some way to be able to allow this kind of interaction. So in all of those cases, we cannot get away with basically, as I said in my introduction, hoping that our assumptions are satisfied. We need to be able to verify in some manner and to bound the performance of that system. So how can we do this? Again, I'm not pretending to present a complete solution, just discussing some ideas and the type of work that we're doing. So basically what we want to do, and again, this is the same kind of thing that you would do in classical control or classical engineering. You want to make sure that if we have a neural network, if you add random noise of some sort or changing conditions of some sort, you're going to end up with an output that has some kind of bounded error. And in particular, some kind of error that is bounded within the limits that are necessary for your operating condition. One difficulty, of course, is that especially when we're looking at continuous inputs and outputs, it's impossible to do that by a discrete observation or by discrete sampling. So this is a kind of a simple-minded example here of an input-output curve, X being the input, Y being the output of the network. And if we sample the output at those red dots, we might have the impression that the output is limited within this gray band, where in fact it is not. It is not. So, and in fact, it's impossible to certify the behavior just by sampling a finite number of points. So how can we do this? So those are three ideas. Again, I'm always very careful in truth in advertisements. So those are just three example ideas that one could look at. One is reachability. And the idea is, in principle, very simple. In practice, much harder. The idea is to say, well, if I know my input is going to be bounded within some region, okay, how does this region propagate through different levels of the system? Okay. Now it's simple in principle. In practice, of course, it is limited to certain architectures. It may require approximations for other architectures, so that's still a very challenging thing to do. But in many cases, it actually can be shown, as in some of the cases that I showed earlier in the videos, it can be shown to provide useful guidance as to the verification of the system. Another idea is based on optimization tools, and the idea is to say, well, maybe I can do a counterfactual kind of approach, meaning I can try to falsify the network by trying to find an example in the input set that will actually be outside of my target output set. Okay, and you can formulate that as an optimization problem under the constraint that the output is outside of the set. This is in general very difficult because of the nature of neural networks, nonlinear and so forth, and this requires approximations. But it has been shown that some useful approximations can be used in this state. The third idea is related to the first one, and it says, well, it might be way too hard to do this kind of thing in general, way too hard to do this kind of thing over the entire input. So maybe we can partition the input first. It's kind of a divide and conquer kind of approach. And look at those smaller pieces first. Of course, the trick is in how to partition the input depending on the problem. And there are, again, a number of approaches for this. So this is just a very quick, I realize I didn't get into too much technical details, but this is just a quick view to give you a flavor of the kind of techniques that we're looking at, and in particular in this work. I should point out that there is a comprehensive toolbox. You see the reference here on the slide from Professor Chanliu Liu and collaborators at Stanford that basically combined all of those approaches to try to have a toolbox for network verification. Let me skip this one. Okay, so this is basically trying to get our hands around the problem of characterizing and verifying, validating the performance of a network. Even if we can do that at runtime, at execution time, there are always going to be situations in which the system is going to encounter an input that is so far out from what it has been trained to do that it cannot produce a feasible output. So this is the typical silly example that I give is if you are driving in your car on the road and you are suddenly surrounded by fog, you immediately, the system, meaning you, immediately knows that your visibility is reduced and that you cannot continue driving in the same mode. So how can you implement that in AI systems? How can we learn or implement a mechanism, a general mechanism that will allow us to detect those conditions and take actions? Now, this is extremely important for a situation that I showed earlier, like with this drone that I showed earlier, where you cannot afford to have even a single failure in the vision of the planning system as the drone moves along. Let me skip a couple of things here. Okay. So one way to do this would be to have an explicit representation of those failure cases, but of course that is untractable. You would have to engineer basically and anticipate all of those outlier cases basically. So the alternative is to have an implicit representation and basically to say, well, maybe I'm going to learn a model that will extract features that are predictive of the performance of the overall system. And that way, maybe I can predict when the system is in a situation where the input is outside of the envelope in which the model would be confident. So let me show you one example of this. Sorry. This is an example from a computer vision task, not a robotics task. And this is basically a basic task of segmentation, right? And what the system is able to do in this case is to automatically figure out that the images on the left are harder to segment than the images on the right. Now, of course, you look at those two sets and, you know, it's obvious. The question is how to do this in a systematic way, in an automatic way, to be able to distinguish those two sets. This is another example on a more robotics context. This is in the context of a mobile robot operating in an outdoor environment. And one of the things that the computer vision system has to do is to do semantic segmentation of the scene and extract the different semantic label in the scene. Obviously, again, the images on the left are much harder to deal with than the images on the right. Okay, and this can be anticipated, we hope, before anything goes through the system. So this is an example here of what I mean by that, a more operational example. Again, looking at a drone system with a monocular vision system. This is how the system looks like. What you see here is the drone flying through an environment, basically a forest. The upper left shows the estimated depth map. This is estimated from monocular vision using a deep learning technique. And the right shows the evaluation of path. This is using what is called a receding horizon technique to, at regular time instant, reevaluate the path to control the drone. Now, the problem here, of course, is that any failure in the vision system is going to lead to a catastrophic failure. So the question is it possible to anticipate conditions in which the vision system is going to perform poorly? The important point here is to anticipate. Once it goes through the system all the way to decision, it is already too late. So the idea here, as I explained earlier, is simply to have training data that will allow us to link the input stream with predicted performance of the system, and to hopefully extract features from the input stream that will help us do that prediction. At training time, the data on which it is trained, if you will, is ground truth on the evaluation of those trajectories. Okay. Now, I'm not going to get into the details of how we get that ground truth, but basically, it's possible, and it's going to give us basically a relationship between the input stream and how well we predict the traversability of different trajectories. Okay. And this is how it looks like in the end. So this is a similar display as the previous one, input stream on the upper left, estimated depth map on the bottom left, and the 3D view on the right. Now, the added component here on the right side here is a scale that will be low if the system is very confident in its environment. It's very confident that it's in an environment that it will perform well in, and it's going to shoot up when it detects a condition in which it reduces its confidence in the system and, in fact, anticipates a possible failure of the system. In that case, by the way, the drone is going to stop, hover for a while until it reacquires a scene that it thinks it can deal with. So this is, again, this idea of not just trusting that the system can deal with any of the input, but actually actively anticipate situations in which it might fail. And one can show, of course, much higher stability of the system and performance of the system. So this is what happens in standard operation. So everything is fine so far. And then here it's going to detect a condition in which the input is corrupted or unreliable, and it's going to recover from that and continue flying. I'm not showing the experiments, but we can show quantitatively a drastic improvement in reliability, as one would expect in using this kind of technique. There is one thing that I mentioned in passing in how this is trained. Excuse me. And I mentioned that it is trained by looking at the output of the task, meaning how those trajectories are evaluated. And this is actually an important thing and a very difficult thing. And let me illustrate this on this example here. This is a different task. This is a semantic segmentation task. Actually, this is a very old screen grab, but you would see the same kind of output now. And one could agree that the example at the top is of much better quality than the example at the bottom. The reason being that there's this significant error here on the wall, this green stuff here, that is mislabeled. So why do we say that the top one is better than the bottom one? Well, that's because the error metric, right, the thing that we optimize in this kind of task, in this kind of semantic segmentation task, is to minimize the number of pixels that are mislabeled. Or conversely, to try as hard as we can to label every pixel correctly. Okay, that's really what we do in those kind of scene interpretation tasks. The problem, of course, is that there is no application, or at least I don't know of any application, at least in robotics autonomous system, that would require us to label every pixel correctly. In fact, that's never needed. So this is an example here where, imagine an autonomous system using this kind of vision system. This is an example here where not only we're using the wrong metric to optimize, to estimate that vision model, we're using one that is presumably much harder than what we actually need to do the task. In other words, for the task of driving, well, we probably don't need to label every pixel correctly, right? The question is, what should be that metric? What should be that task-oriented, that task-level metric? Okay, and this is a major impediment in making progress when we look at building system-level operations, right? It's fine when you're interested in the computer vision piece, just the semantic segmentation, just getting the pixels right. It's not fine if now you want to embed that into a much larger system. Now, this was the case in what I just showed, right? I mean, one thing that we could have done is to say, you know, to evaluate how accurate is the 3D world that is reconstructed by the vision system. But the thing is, we don't care if it's 1 millimeter accurate or 3 millimeter accurate. The only thing we care about is how accurately it evaluates the trajectory from the control system. That's the only thing we care about. How can we design the entire system so that we actually optimize that metric and not this intermediate vision box? It's relatively easy in this drone case, although even then the training is quite involved in terms of the setup. It's also easy in some robotics application like grasping. So in this case, the metric is whether the robot grasps or doesn't grasp the object. So it can be quantified and coded relatively easily. It is very hard for anything that is more complex, especially anything that has more complex decision making, higher symbolic interaction, and so forth. There is one example here of language-based interaction with a robot. So this is a major issue, this idea of optimizing the right metric, even though that was one of my implicit assumptions, right? We assume that you know, labeling the pixels in the image is the right thing to do, it's the right metric to optimize. So we always make those assumptions, but this is, I mean, the right metric is actually a major issue. Okay, and the last thing that I will mention, by the way, Isabel, can you remind me how much time I have left? Because I might be getting overboard there.
Oh, 5 minutes, it's okay?
5 minutes, yeah, that should be okay. Thank you. So the last thing I want to mention is this other implicit assumption that I mentioned about the input being consistent with the training conditions. Or more precisely, to have the model being able to handle all of the conditions that are presented to it at once. And of course, in many cases, that assumption is violated. So let me give you an example here in the context of drone. And in fact, this is, should I mention that this is an example from Professor Basti Scherer, and you have here the pointer to his group if you want to see more details on this kind of thing. So let me again look at an example having to do with drones. And if you look at those different environments, this is one environment here, semi-cluttered outdoors, difficult things with power lines and things like this. This is another environment with a completely different kind of kinodynamics requirements and so forth. And this is another environment, much more cluttered, actually very cluttered, requiring, again, different constraints on the planning and the control of the drone. Okay. Now, the reason for showing you those three examples is to point out that even for single task, flying, depending on the environment, and admittedly those were a little bit extreme example, but still, depending on the environment, we're going to need very different strategies, very different approaches. In this case, very different approaches to the control and planning system on the drone. All right. Now, we could think of having a single monolithic way of doing this, but that's probably not going to work because it would have to encompass such a large range of conditions that it is simply not practical and simply not feasible. So what we need to do is to have some kind of way to learn how to select those different approaches and those different strategies. In this case, this means being able to dynamically select between different planning strategies. Okay. More generally, the reason why I mentioned this example is to basically plant the seed for this discussion about the need to have this selection strategy across multiple models. And that this implicit assumption that we make in many systems that, if the model has enough capacity and generalizes enough and so forth, it should be able to handle a large set of operating conditions is generally not correct. And that we need to do this kind of thing, which is this adaptive selection of models. So one way to do this would be to generate, in this example of the drone, to generate a number of worlds, to try a number of different planning strategies, and to learn how to select the right planning strategy based on what we see in the world. In reality, that does not work well, and in fact, this is part of the reason why those kind of things are challenging and part of the research in this area. This is an example here where on the left, the blue planner is going to perform well. It's what we call a precision planner that will go through that small opening here, and this is the best way of doing the planning in this case. But the observation here is that if we move this red obstacle here just a little bit, so in other words, a small perturbation of the input is going to cause a large change in the output, specifically that now this planner 1, the blue planner, is now infeasible and it will not find a solution. Okay, so the higher level point here is that a simple-minded approach to those kind of problems, those kind of selection problem that says, well, I'm going to basically learn a strategy so that I can decide which model to use, typically will not work. We have to, in fact, choose collections of models, and this is just a graphical example of how that would work. You start with your training data, you train one predictor that's going to predict those the best strategy or the best model for that training data, but of course it's going to fail on some of that data. So now you're going to take those failure cases and now train a second predictor that's going to train to generate another model and do this again. There are some theoretical results that show that if you do this right, you have some guarantees as to the probability of having a correct model, or a model that will succeed in the task in the end by training the system in this way. So this is just again a high-level view of the problem, of this selection problem. Basically, the idea of getting around the challenge that a single model cannot handle all of the operating conditions. Let me show you a couple of examples of this. Those are a couple of operational examples of this on the drone. Those are two different examples here, two different environments, I'm sorry. One is a more cluttered example on the right, which requires lower speed, less clearance around the obstacle. And the left one is a more open example, okay, that will allow for a higher speed but lower curvature driving. Okay, so those are kind of examples to visually frame what we're talking about here. By the way, this has been deployed. This is truly operational. This is an example here on a much larger drone flying outside, and this has been similar ideas have been deployed on autonomous helicopters and larger systems. Okay, And of course, by doing this, one can quantify that, and one can show a massive boost in the performance of the system. Performance of the system meaning essentially mean time between manual intervention, as you can see on the numbers here. This is another view of the situation here. The rectangle at the top, sorry, I don't have a pointer here, but the rectangle at the top here shows a timeline, basically the time steps as the vehicle is moving through the environment. And the vertical axis shows which of the planning strategies are active at any given time. And basically what happens here is every few milliseconds or so, the system reevaluates its strategies using the learn selection that I showed earlier, and switches between those strategies as needed. And those are two snapshots here where two very different planning strategies are used in two different environments, one requiring a more specialized planner to go close to to a goal that is close to an obstacle on the right, and using a more conventional approaches on the left. Okay, so again, this was a little bit, maybe too much detail on this, but this was again this idea that the implicit assumption that we have that if a model is complex enough or general enough in some sense, it can handle all of the operational situation is wrong, and that in real systems such as this one, we actually need to have different models for different operating conditions, and we need to be able to learn how to make decisions about those models based on the input. All right, so this is basically what I wanted to talk to you about, basically giving you a little bit of a sample of some of the things that we look at in trying to fight essentially those implicit assumptions that we make in those type of systems. And I think I will stop here.
Thank you very much, Martial, for these very interesting talks. We have a few questions. So, oh, sorry, I forgot. Yes. So I don't know if you saw them because. So first.
No, I was seeing only my presentation on my full screen.
Okay.
I was not seeing anybody.
The first one is from Mr. PRAIRIE-PSAI. Sorry. And I'm sorry, I cannot, the system tells me that I cannot give you the microphone, so I will just read your question. He says, you use GAN to generate data in situation or data quantity is not enough. However, GAN approach need many data to be trained. It seems not clear why GAN help in this situation, like a snake biting its own tail.
Yeah, good question. The reason why we don't have that problem is because I call that a generator, but it's not a GAN. In other words, it does not use the same adversarial generator loss that a GAN uses. What drives the training of the generator is the performance of the output test, which is different than a GAN. So that's why we don't run into this problem. The other point that is important here is that when I showed the slide for convenience, for graphical convenience, I put a picture as the output of the GAN, the output of the generator, sorry, not the GAN, the generator. But in fact, what is generated is not a picture input. It's actually a feature vector. And that's also an important difference. Okay. I can't hear you anymore, though.
Sorry.
Yeah.
Next question I will take from Gerard Burnside. I don't know if I can see him. Otherwise, I will read the question. It seems that it doesn't work. So I will read the question. In the last example, how do you decide that you have trained enough planners?
Right. So this is decided on the training set when we are able to address all of the training examples. It's basically the target.
Thank you. So next question is from Jean Ponce. I would like to be able to invite people, but it just doesn't seem to work. Yes, it works.
Bonjour.
Hello.
Yes.
So my question is at the beginning. You said, if I understood correctly, that in many vision tasks, at least, very few images are available at training time. And to me, that's not obvious. And it's not a natural thing to have lots of data at training time. To me, it's not obvious. The annotation may be very sparse or maybe inexistent, but data will be abundant, I think.
No, I disagree with that. There is something called the zip flow that shows that you have an exponential decay in the number of occurrence of objects. And so you're right, you could, in theory, you could work really, really hard to acquire lots of data, even on those rare occurrences. From a practical standpoint, that simply is not going to happen. You're going to have very few examples.
But even for people, we see stuff all the time. We see continuously 12 hours a day the world, and we move through the world, so we see it through different viewpoints, with changing conditions. And I have no idea, I'm not psychologist, I have no idea how good we are at recognizing quickly objects we have seen once or twice. So I don't know how much of a real problem this is.
Well, again, I still think it's a real problem. I'm not going to make any claim about psychology, about the human vision system works and all this. I have no idea, and I make no claim of this. From a purely engineering standpoint, however, you will never be able to acquire enough data on most of the example. This is in fact a growing subfield, long tail learning and that kind of thing, and so. Even if you just discard for a minute anything having to do with the actual vision system and cognitive system, right? Even as a purely practical matter, you need to address that problem.
Thank you. Next question is from Robin Strudel. I cannot invite him again. In the semantic segmentation task, you suggested that metrics such as pixel accuracy are not good and are not good ones. Do you have suggestions or pointers about better metrics?
No, that's exactly the problem. That was exactly my point, right? I mean, the pixel labeling is of course a great metric if you're interested in the vision task of, well, it's a circular argument actually, of labeling the pixels, right? But now, if all you're interested in is using that output to perform another task, driving or something, or interacting with a person or something else, then in that case, that metric is not the right one. And again, it's a much harder, much more stringent goal for the vision system than what's actually needed for the task. And to answer your question, no, I don't know. I was posing the problem. I don't have a solution to that problem. And I think there's something to be studied and to be discovered as to how we can design a better task-based metric that would be more effective. But I don't have a solution to that. No.
Thank you. So next question is maybe last question is from Nicolas Torres. Could you comment on the difficulties of achieving bounded stable controllers and how much adoption do they have in industry, particularly due to safety considerations like in human-robot interactions? Yeah,
I think so. I can't comment too much on that, but except to say that I don't think we are still we have reached a level where we have reliable enough certification tools, even of this nature, in terms of the human interaction. And so, by the way, again, truth in advertisement. Some of the examples I showed are progress in this direction, but certainly not yet at the level the level of certification that we would want.
So I think we are done with the questions. So I would just like to thank you again, Martial. It was a great honor to have you today for this first session. Thank you, everybody, to be here and to join us for this talk. Next time will be on March 3. We will receive Yann Lequin from NYU and Facebook. And the next talk will be in April 7 from Odiliva from MIT. So thank you, everybody, and see you next time.